So welcome to They're Coming for Your Tools, Exploiting Design Flaws for Active Intrusion Prevention. I am John Ventura, and I am part of Optiv's research practice. I was also a member of ISS X-Force back in the day, and along the way I've done some malware research, and I think that's informed a certain perspective that you'll see on display here. So we are targeting design flaws in popular attack tools and methodologies, and we're doing this as a means of intrusion prevention. Sometimes people break into computers, attackers, pen testers, people I can't even imagine, and this set of people, they face common problems, and sometimes people solve those problems by creating software, and when they do that well, when those solutions are effective, those software packages often become popular. And just like any other software out there, those software packages exhibit vulnerabilities, and it's the exploitation of those vulnerabilities which is a path towards improved intrusion prevention. And you can do this with little cost. So this is a talk for both blue teams and red teams. So if you're part of a blue team and it's your job to defend networks, to defend computers, I'm talking to you. You need to know that you can exploit these design flaws as a means of intrusion prevention. You can turn the tables on the bad guys. You can exploit vulnerabilities in their software for a change. You can do proactive responses, and we'll show you how to do that here. If you're a red teamer like these guys and you break into computers for whatever reason, you have to know that just like any other piece of software that you introduce into a network environment, your tools bring with them a certain set of vulnerabilities. You cannot treat your tools as a magic black box. You really need to be careful with how you do these things, especially if you're a pen tester. If you are not careful, you could potentially get your clients compromised due to your actions. This is some pretty serious stuff. And on the other side of that coin, if you're so inclined, you can target other attackers. You can steal their shells, make them do your hacking for you. I think there's some laws there. So we're going to be talking about two different strategies for this today. The first of which is going to be man-in-the-middle counterattacks against insecure command and control channels, and specifically we'll be touching on Meterpreter and PowerShell Empire, and we'll talk about a few others. And after that, we will discuss some countermeasures against brute force password recovery. So if you are using NBNS or LMNR spoofing to steal people's hashes, we're going to make that harder. And if you are trying to steal somebody's pre-shared key on a wireless network, we're going to make that harder too. So this isn't just theory. We are releasing proof of concept tools to demonstrate these techniques. You can download them, use them at home. We wrote these in C. We wrote these to be really compact and small, and if you ran them all together at once, even the ones that we aren't showing here, they would take up less than 200K of memory. So if for some reason you're still using a Commodore 64, it might be time to upgrade or consider maybe running them one at a time. Those upgrades, they don't necessarily have to be expensive. The whole point there being you can use so-called next-gen security solutions. You can do that on the cheap. It doesn't necessarily have to come in a multi-thousand-dollar magic box. You can do this cheaply, but don't tell the guys in the vendor hall I just said that, because they're great. So let's talk about those command and control channels. If you want two computers to talk to each other in a secure way, and they've never talked to each other before, this is a surprisingly difficult challenge. And if you want to get an idea of what I mean, consider TLS-SSL or OpenSSL in particular. Some really smart people have been working on those efforts now for decades. And occasionally, significant vulnerabilities still show up, and a lot of them even have catchy names. So if you consider the scope and breadth of that community and all the effort that's gone into that, that is a tremendous head start on any communication channel you are likely to develop yourself. So if you still want to take that on, best of luck to you. But in the real world, there are almost always man-in-the-middle attacks, and let's talk about some of those right now. The first of these software packages that we looked at was Meterpreter, which is part of the Metasploit framework. And this diagram that you see in front of you is a representation of the typical staging scenario for Meterpreter. I say typical because there is a so-called paranoid mode that uses TLS, SSL, and certificate pinning, and it is not necessarily the easiest thing in the world. It takes extra configuration steps. You need to use third-party binaries, the OpenSSL command line in particular. It is not necessarily intuitive for a lot of people, and you won't even see it documented in a lot of the how-to or getting started guides. And I'm not even sure it works in some real world situations, like if you're going to go through someone else's proxy, or if you're going to embed Meterpreter within an exploit like MSO8067, it's not the easiest thing to do. So most people are going to opt for this what you see here. And in this diagram, Meterpreter or Metasploit is represented by the Metasploit logo, and the machine being compromised today is the HAL 9000. These arrows in between them are a TCP connection, and the first thing that gets transmitted across that TCP connection is a TCP segment that has a 32-bit or 4-byte payload length field. Following that, there's a slight pause, and then the actual payload itself gets transmitted, and that payload is the Meterpreter client. When HAL gets that payload length field, he allocates a certain chunk of memory that is going to be equal to or greater than that payload length, and then he waits for that payload to come across. When he gets the payload, he copies it into that chunk of memory that he just allocated, and then switches execution there, thereby running the Meterpreter client, and the Meterpreter control channel gets established, and that bottom arrow exists. And this is what we can do about it. In this diagram, this is our response, and you get to be Dave Bowman, the star child himself. And Dave is running a proof of concept sniffer that we developed to demonstrate this man-in-the-middle counterattack. And that proof of concept sniffer looks at all the TCP segments it can, and it looks for payload length segments that it recognizes. And what's nice about those payload length segments is that they are relatively static. So if you are staging with a Microsoft Windows 64-bit machine, for example, that payload length field is likely to be a certain value. And the sniffer knows about many of those values. And when it sees a payload length TCP segment that it recognizes, it takes these sequence numbers from that segment, and it anticipates what the sequence numbers will be for the payload. And then it uses packet spoofing to inject a custom payload with friendlier software. So because there is that nice pause between the transmission of the payload length and the transmission of the payload, Dave Bowman's packets are going to get there first, and HAL 9000 looks at those packets, see the sequence numbers are in order, the source and destination data is in order. HAL just assumes that's probably part of the TCP connection, and when those actual Meterpreter payload packets come across, well, those sequence numbers appear to be retransmissions, and that software gets ignored. So when it comes time to copy that data from the line over to the chunk of memory for future execution, it's Dave's software that gets run and not Meterpreter. And by default, the software that we include is a simple reverse shell. So when it comes time to run that client, Dave Bowman gets a reverse shell. To further illustrate what we mean, here's a snippet of the configuration file that we distribute by default. And you can see these trigger tags. Those define the contents of that payload length field. The first 4 bytes are the payload length. Now you might note 2 trailing null bytes there. Those exist because Windows sometimes does padding because alignment's important, and we account for that here. And the response, that's the data that we're injecting into the TCP stream. This is shell code. It's position independent code. It is a simple run-of-the-mill connect back shell. And the next slide is going to show us what Dave Bowman is going to see. And we grepped out the console tags from that configuration file. That's Dave's IP. That's where that command and control channel is going to be redirected. And Dave is running the sniffer in the background, and that netcat listener is waiting for staging to occur. Dave is going to get a shell as soon as staging occurs, and there it is. Dave Bowman has a shell on the HAL 9000, and the Meterpreter user has nothing. And here is what it looks like from the Meterpreter user's point of view. This is a Metasploit console and just a simple handler, and I'm going to redirect your attention to the last 2 lines of this terminal. And the second to last line is what the user sees, what the Meterpreter user sees when that payload length segment gets transmitted. And you can see the payload length segment up there. It's in base 10. And right after that, you should note an error message. When we did our magic with the packet spoofing and the sequence numbers, we kind of messed up that TCP connection between the 2 nodes. I like that. We could have written in some RSTs to reset that TCP connection, but you know what? I would rather have our adversary here have an error message, have a broken TCP connection, instead of the Meterpreter prompt that presumably he wants. But we didn't stop there. When you tell people that you are targeting Meterpreter for man-in-the-middle attacks, a lot of people will tell you that they have moved on to PowerShell Empire. PowerShell Empire is really well designed. It's earned its fan base. This is some feature-rich software, and there are 2 currently supported branches of PowerShell Empire. There's version 1.6 and there's version 2.0. They both do payload encryption or obfuscation somewhat differently, and they're both vulnerable. So when we did the man-in-the-middle counterattack, we targeted the initial portions of staging, and you can see that here in this graphic that we borrowed from PowerShell Empire's website. Later on, you can see some really nice cryptographic features. There's public keys and private keys. There's Diffie-Hellman and AES and some really good stuff, but we don't mess with any of that. We just hit them right at the beginning, and we broke down this man-in-the-middle counterattack into a 3-step process. And that first step happens right when the Empire user tries to introduce the PowerShell Empire software into a compromised machine. And if you've done this in the real world, you know that you have to submit a command line that starts with PowerShell.exe and includes this crazy base64 blob of PowerShell code. And that code gets executed, and what that script has one job. What it does is it goes out to the staging server via HTTP and downloads an encrypted or obfuscated payload, then decrypts it or deobfuscates it using a shared secret, using a symmetric key, and then executes whatever it gets back. There are no checksums, there's no integrity checks, no signatures, and we take advantage of that in step 2. So because 1.6 and 2.0 both handle their payloads a little bit differently, we had to handle the payloads a little bit differently. In both cases, we take a live payload from the staging server and then repackage it with our own software. For version 1.6, that payload is obfuscated with XOR, and the key is an ASCII representation of a large hexadecimal number, and because it's hex, for any given offset within that key, there's only 16 possibilities. There's 0 through 9 and there's A through F, kind of limited, and the payload itself is a little predictable. And by that I mean, we know it's a PowerShell script, and with a little bit of analysis, we know what characters are going to occur, and we know roundabout what the frequencies of occurrence of those characters are. So we take that knowledge, the frequencies of the characters, and the limited key space for the key, and we do a little bit of statistical analysis, and we extract the key from that obfuscated payload. A little bit counterintuitive, but it works really well. Once we have that key, we repackage it with our own payload. For version 2.0, the story is a little bit more complicated because 2.0 uses RC4 for encryption. And the nice thing about RC4, or the horrible thing about RC4, depending on your perspective, is that it is vulnerable to man-in-the-middle attacks. Specifically, if you know the contents of that plain text, you can make that encrypted message say anything you want it to say. You can see in the bullet points, you can see how that attack works. This is a classic crypto attack. I wish I was the guy that discovered it. I wish I was showing you something new, but this classic attack still works. And that's a known, the plain text is a known payload because PowerShell Empire is open source. Everybody has the source. That's source code in there. We all have it. And for either version, we repackage that. We repackage the software that the user wants stage 2 to be, and we repackage it as our own. And then we use a man-in-the-middle packet spoofing attack like what you saw earlier with Dave Bowman and the HAL 9000 to overwrite the responses from the server. So when that base64 encoded script reaches out to the staging server to try to get the next stage script, it will end up getting our software because we overwrite it on the line. And this is what it looks like from our point of view. The software is somewhat flexible, and it lets you define what software you want to run on the compromised machine. Today, because it's a proof of concept, we're going to launch calc.exe because that's what proof of concepts do. By default, the software that it sends along is a reverse shell, but you know, calc.exe, it's a proof of concept. So in the command line here, you see that we are reaching out to the staging server via HTTP. There's other ways you could do this. You could sniff that payload. You could get it through your proxy logs. We chose HTTP. There's other ways to do it. And here's what it looks like from the attacker's point of view. This attacker sends the PowerShell staging command, and PowerShell does not stage. This user gets calc.exe. We should note at this point that it is a little bit abnormal in practice to launch PowerShell Empire from a GUI. You don't normally get to do that, but you know, I wanted to show you guys calc.exe. We didn't stop there though. There were a couple other software packages that I think deserve a mention. In particular, Fuzzbunch, which includes the double pulsar module. This is part of the Shadow Brokers dump. The Shadow Brokers leaked some software that was developed by and/or for one of these 3 government agencies, and I'm not going to speculate which one. And the people at Countercept released some really in-depth analysis of that software, and as it turns out, double pulsar is very easy to detect on the line. There are snort rules that can detect it. It uses XOR for encryption, exposes the key in plain text, And to make matters worse, double pulsar does not really have adequate authentication once you've introduced it onto somebody's computer. So if you ever detect double pulsar running, feel free to fire up your own double pulsar client and follow that guy in, because there's nothing's going to stop you, even if you don't have the exploit. This is not safe. Don't use it, especially if you're a pen tester. Just say no. On the other end of that spectrum is Cobalt Strike, which has several staging and even some stageless options. There are data integrity checks, and to their credit, Raphael Mudge put out a blog post that talks about these issues in depth, and we don't have time to go into it today, but if you're a Cobalt Strike user, I strongly recommend you RTFM. In the meantime, let's switch gears and let's talk about password cracking and what you can do about it. So password cracking is computationally intensive, and you can see a really nice password cracking array that this picture was donated by my colleague Matt Wagenknecht, and when Matt wants to crack passwords, he throws his password hashes into this array of high-end GPU-enabled graphics cards, and they crunch on these passwords. This is computationally intensive. Even the power consumption, if you're doing this seriously, is noteworthy, and we're going to make it harder today. So we took on LMNR and NBNS spoofing attacks. These attacks are really effective and really popular. This is what pen testers typically do on a Monday morning when they show up on site. These attacks are really effective with a little bit of luck, not even that much luck. The pen tester might even have domain admin by lunchtime. Laurent Gaffey's responder script made this attack popular. We can detect it, we can disrupt it. Responder is a great piece of software, but here we go. In order to understand what we're doing, here is a diagram that explains how the attack works. This sad machine here in the center of all these blue arrows is a typically misconfigured Microsoft Windows machine. And when it wants to do name resolution, the first thing it does is DNS. And if DNS fails, it sends out these broadcast UDP packets via NBNS and LMNR. And it asks everyone on the network, hey, are you this machine? And the evil guy here, when he gets these queries, he responds back universally and says, yes, I am that user, and the bad guy is hoping the other side of this diagram happens. The bad guy hopes that the misconfigured Microsoft Windows machine will connect to it on some supported protocol, and with a little bit of luck expose a plain text password with slightly less luck. The bad guy is hoping to use NTLM to induce that misconfigured machine to send a password hash. And this is our response. So just as with the typically misconfigured Microsoft Windows machine, we also send out NBNS and LMNR queries. The difference being, we're not actually looking for another machine. Our queries are for machine names that are 16 to 20 bytes in length of random characters. And anybody responds to that and says, yes, that pile of garbage is in fact my machine name, we consider that entity to be hostile. And because that entity is looking for password hashes, we send password hashes. We also log the alert. So we go beyond logging, we actually do something about the attack. And here's what it looks like from the defender's point of view. This command line, it takes usernames and passwords from that usernames.txt file. Presumably these are fake usernames and passwords. However, people have talked to me about canary accounts and using that as a means of detecting relay attacks if you're worried about that. And we send credentials, hash credentials from that list, and we log the alert, and we look for these bad guys every 10 seconds. And it's a little bit more exciting from the responder user's point of view. Here's responder, and there we go. The bad guy just got a password hash from Dennis Ritchie. Earlier, the bad guy got a password hash from Grace Hopper. If we wait long enough, we'll see a network guy. Perhaps that's John Postel. Sadly, everybody I've just name checked right there has passed away, so it is unlikely that any of them are going to be using NTLM or any network-based services at all. Again, these are fake accounts, and we are hoping that the attacker jumps onto the hamster wheel that we've just constructed. And again, the software is designed to work around your strategies, so if you want to be a little bit more aggressive, we include a resource exhaustion attack. So this bad guy wants some hashes, let's send him some hashes. If the bad guy walks away from the console, the bad guy walks away from the console, the bad guy comes back, that hard drive's filled up, that database of hashes is somewhat corrupt. It's a bad day for the bad guy. And we also took on WPA2 attacks designed to steal that pre-shared key, that wireless password. And in order to understand how that attack works, we need a little bit of a discussion of the handshaking process that happens when you want to join a wireless network. The STA in this diagram is the node that wants to join the network. So if you imagine a cell phone or a laptop, that wants to join the network. The AP is the access point wireless router or whatever controls that wireless network. And you can see in between them there's a four-way handshake that happens. And that four-way handshake involves both ends generating a nonce, and those nonces are used together with the actual pre-shared key to construct a message identification code, or MIC, which is ostensibly a hash of that pre-shared key. And the attacker software, real world, when they're doing this, the attacker is going to sniff packets from a lot of different networks, and they're all differentiated by looking at the BSSID or MAC address of those APs. So what we do is we mimic this authentication process. We do packet spoofing to send out fake handshakes with the same MAC address of that AP and fake passwords. So we frustrate password cracking from that perspective. And I know a lot of people test out wireless security tools on their neighbors' networks, and I'm not naming names. But today I recorded this at home, and we're going to defend my neighbor's network. I don't know Mr. Garcia. If you ever see this, Mr. Garcia, thank you for allowing me to defend your network. This defense is actually really, really passive, so Mr. Garcia can go ahead and watch his cat videos on YouTube. He never knew this happened. And I don't know Mr. Garcia's password, so we're going to use a fake password. And this bad guy is going to use AeroDump, a pretty common tool for this, and he's going to target Mr. Garcia. And anybody who's done this attack real world knows that there's a lot of waiting. There are deauth attacks if these handshakes don't happen on your schedule, but even then those deauth attacks aren't necessarily easy. Now we got a handshake, and the bad guy's going to try to crack that password. You see, there we go. The bad guy got the fake password, whatever Mr. Garcia's real password is, the bad guy's going to have to go back to square one and try to get it. Again, the bad guy just has to do a lot more waiting. And if you imagine you put in 4 fake handshakes and the bad guy gets lucky and gets 1 real handshake, the bad guy either has to figure out how to tell the difference between the handshakes or crack them all. And if the bad guy chooses to crack them all, you've just degraded their cracking capabilities by about 80%. And as you can see, I was only able to crack about 1,000 guesses per second. That is really slow. So we've made it harder to steal Wi-Fi passwords, and we did it on the cheap without really disturbing Mr. Garcia. So we intend to continue this project into the future. There's areas we can keep going. We can integrate the wireless defenses with OpenWRT or other available access point software. Existing security technologies, especially IDSs and IPSs, you can definitely put this in there. It was designed for that. Proxies, if you have a smart proxy, we can make it smarter. In the future tools, we want to target whatever the cool new tool is that people are using to break into computers. That's what we want to go after. So if you want these tools at home, if you want to try this at home, there's the GitHub for the Salad project. This is the Seek, Locate, Destroy toolkit, otherwise known as the Salad project. If you want to reach out to me, if you're curious, or if you want to see how this is going, here's my Twitter handle, John A. Ventura, and thank you for your time today.